Good evening, my dear students. இந்த Lagrangian equation of motion அப்படின்றது கொஞ்சம் லென்த்தியான டெரிவேஷன். நீங்கள் இந்த கிளாஸ் அட்டன் பண்ணுறதுக்கு முன்னாடி நீங்கள் எம்எஸ்சி ஃபஸ்ட் எம்எஸ்சி படிக்கிற ஸ்டூடெண்ட்டாக இருந்தாலும் சரி, இல்லை டிஆர்பிக்கு ப்ரிப்பேர் பண்ணுற ஸ்டூடெண்ட்டாக இருந்தாலும் சரி, இல்லை வேறு யாராவது கிளாஸ் எடுக்க போகிறவங்களாக இருந்தாலும் சரி, தயவு செய்து ஒரு நோட்டு பென்னோட எடுத்து உங்கள் கூட வச்சுக்கோங்க. அதுக்கப்புறம் நான் எழுதுகிற ஒவ்வொரு ஸ்டெப்பையும் நீங்களும் எழுதி கவனிங்க. அப்போ உங்களுக்கு ஈஸியாக புரியும். என்னோடய எம்எஸ்சி ஸ்டூடெண்ட்டாக இருந்தீங்கன்னா நீங்கள் ஆல்ரெடி எழுதியிருக்கிற நோட்ஸை இந்த நோட்ஸோடு கம்பேர் பண்ணுங்கள். சில ஸ்டெப்ஸ் எல்லாமே நான் உங்களுக்கு ஷார்ட்டாக கொடுத்துருப்பேன் நோட்ஸ் கொடுக்கும்பொழுது. இதில் கொஞ்சம் அதுக்கு எக்ஸ்ப்ளனேஷன்லாம் கொடுத்துருப்பேன். நீங்கள் அதுக்கு பக்கத்துலேயே அந்த நோட் போட்டு எழுதி வச்சுக்கலாம். ஒரு சில மேத்தமேட்டிக்கல் ஸ்டெப்ஸ் எல்லாம் இதில் எக்ஸ்பிளைன் பண்ணியிருப்பேன். அதெல்லாம் நீங்கள் கவனித்து ஸ்டெப் பை ஸ்டெப்பாக அண்டர்ஸ்டாண்ட் பண்ணிக்க ட்ரை பண்ணுங்கள். பொறுமையாக இது ஒரு ½ வீடியோவாக இருக்குது. இதை ஃபாஸ்ட்டாக என்னால் செய்ய முடியாது. ஏன்னா ரொம்ப கவனமாக டெரைவ் பண்ண வேண்டிய ஒரு விஷயம். ஒரு சின்ன மிஸ்டேக் வந்தால் கூட மறுபடியும் முதல்லேருந்து ஸ்டார்ட் பண்ணணும். அதனால் ரொம்ப பொறுமையாக தான் போயிருப்பேன். நீங்களும் அதை ஃபாலோ பண்ணி ஒரு தடவை கவனிச்சிட்டிங்கன்னா இது உங்கள் மைண்டில் பதிஞ்சிடும். அதுக்கப்புறம் இந்த ஈக்குவேஷன் எப்போ பார்த்தாலும் உங்களுக்கு ஈஸியாகவே இருக்கும். அதனால் பொறுமையாக உட்காந்து இந்த கிளாஸ் அட்டன் பண்ணி அதை பயன்படுத்திக்கங்க. ஓகே. Good evening, my dear students. In this video we are going to discuss about a Lagrangian equation of motion based on D'Alembert's principle. Already we discussed about D'Alembert's principle in previous video. You should remember that, because if we can apply D'Alembert's principle to a system, it should be constrained and it should be halonomic. What is the meaning of constraint? Let us consider a free particle. We want to restrict the moment of a particle. It is some external factor is involved with the moment of the particle. Now it is subjected to a constraint. And halonomic means the moment of a particle in halonomic system only connected with the configuration. That means configuration of a particle. So time does not involved with the moment of the particle in halonomic. That is called a halonomic system. Now we are going to discuss about the Lagrangian equation of motion based on the D'Alembert's principle for a constrained particle. Now we can write the transformation equation first. Transformation equation, that is Ri equal to Ri Q1 Q2 Qn T. So this is the transformation equation for a generalized coordinate system. Now the change in position is called dRi by dt. So the change in position with respect to t is equal to, we can write the differential form of this transformation equation, because more than one coordinates are involved with the position of the particle with respect to t. Therefore we can apply the partial differentiation here. Now the Ri change with respect to Q1, then we can write dou Ri divided by dou Q1, this is, and Q1 change with respect to q1 change with respect to time, that is dq1 divided by dt. So like that, again we can differentiate with respect to q2 dou ri by dou q2 dq2 divided by dt plus and so on, then dou ri by dou t dt by dt. This is the differential form of the transformation equation. This is equation 1. Now we can write another transformation equation. With respect to ith and jth group of particles, then Ri equal to Ri Qi Qn, capital N, and Qj dot dot Q small n comma t. Here I equal to 1 2 3 n, j is represented 1 2 3 to small n. So ith group of particle, this is jth group of particle. So this is the transformation equation with respect to jth and ith particle. Now we can write the velocity of ith particle with respect to j. Therefore dri by dt, that is equal to vi, that is equal to sum over j dou ri divided by dou qj, and then dqj divided by dt plus similarly dou ri by dou t dt by dt. This is equation 2. Already we told from the beginning of this question, the system is involved with constraint. Okay, so the virtual displacement is also involved with the particle of the system. Then for infinitesimal displacement. Infinitesimal displacement means a small deviation, a small variation in the position of the particle. It is not countable because it is very very low value. It is not measurable. That is called infinitesimal displacement. We can mention that del Ri is the infinitesimal displacement. It can be involved with del Qj. Now we can write the virtual displacement of the ith particle with respect to j. Then del Ri equal to sum over j, because the ith particle change with respect to j, therefore sum over j dou Ri divided by dou Qj del Qj plus dou Ri by dou t and del t. This is the virtual displacement of the ith particle with respect to j. This equation is 1 2 3. But we know that very well the virtual displacement does not involved with time, therefore this term is 0. Therefore the virtual displacement does not depend on time. Therefore we can write this equation dou Ri divided by dou t del t, that is equal to 0. Then the equation 3 reduced to del Ri is equal to sum over j dou Ri divided by dou Qj del Qj. So this equation is 4. But already we know that the D'Alembert's principle involved with the actual force, the D'Alembert's principle says that minus pi dot, that means reversed inertial force is involved with the system of particle. Therefore we can write according to the D'Alembert's principle sum over I Fi minus pi dot del r equal to del Ri equal to 0. So now we get the value of d del Ri from equation 4. Now we can substitute the equation sum over I Fi minus pi dot into sum over j dou Ri by dou Qj del Qj is equal to 0. Now we can expand this equation like this: sum over Ij Fi and dou Ri by dou Qj del Qj minus then sum over Ij pi dot dou Ri by dou Qj del Qj equal to 0. Now we can separate the term from the first term in the equation. Sum over I Fi dou Ri by dou Qj is equal to Qj, that is Qj. Therefore we can write the above equation as sum over j. Already we separate the sum over I with this term, therefore remaining is sum over j here, and then this term is replaced by Qj. Therefore we can apply Qj del Qj minus sum over Ij pi dot dou Ri by dou Qj del Qj equal to 0. So this equation is 6th. And the this equation is 5. Okay, now we take the second term of this equation 6. From equation 6 we can write sum over I j p I dot dou ri by dou qj del qj, that is equal to, we can write the pi dot, we know that p equal to mv, we can also write it as m r dot, then p dot is m r double dot. Therefore simply we can write the equation as sum over I j m r double dot dou ri by dou qj del qj, and we can write m r double dot is also d by dt m r dot. Okay, now we can apply this term in this equation. We can get sum over I j d by dt of m r dot dou ri divided by dou qj del qj. Now we can apply the differential rule. Here we take here u and v, therefore we can expand this equation I j u, that is u m r dot u dv m r dot d by dt dou ri by dou qj u dv plus v du, that is v means dou ri by dou qj v du, then d by dt u is m r dot del qj. Okay, now we can rearrange the equation, then we get sum over ij, the term is shifted here, d by dt m r dot dou ri by dou qj minus m r dot d by dt dou ri by dou qj del qj. And put here the bracket, and we can also apply r dot is equal to v, r dot is equal to v, that means velocity. Therefore sum over ij d by dt mv dot dou ri by dou qj minus mv d by dt dou ri by dou qj del qj. So please make the correction here, ri, here ri, Ri, here Ri, and here also Vi. So this is the correct form. Okay. So this is the equation 7. This is equation 7. Now we can derive the separate solution for d by dt dou r by dou qj. Then we can write the equation separately from equation 7. From equation 7, d by dt dou ri by dou qj, that is equal to sum over k. Here the jth particle differentiate with respect to the k. Therefore, let me take dou ri by dou qj as, see here, like ri. Therefore, we can easily differentiate this equation with respect to k. Therefore, sum over k we put here dou by dou qk and dou ri divided by dou qj, dou by dou qk. Actually we can write the equation dou ri by dou qk. Here ri, we take ri as dou ri by dou qj. Therefore we wrote like this. Okay, and then dou qk divided by dou t, and then dou by dou t dou ri divided by dou qj dt divided by dt. Or we can rewrite the equation as sum over k dou square ri divided by dou qk and dou qj, dou qk divided by dou t plus dou square ri divided by dou qj dou t dot dt by dt. Then we can take out the common term in the equation dou by dou qj, dou by dou qj, and then the equation take the form dou ri divided by dou qk and dou qk divided by dou t plus dou ri divided by dou t dot dt by dt. We put the bracket here. Now this term is similar to equation 1. Therefore we can substitute, we can replace this term by dri by dt. Therefore we can write the equation dou by dou qj dri by dt, that is equal to dou v divided by dou qj, because Ri is the position change with respect to t, it gives velocity. Therefore dou v by dou qj is the solution for the term d by dt of dou Ri by dou qj. This is equation 8. Here put vi, and also the differentiating the transformation equation, the transformation equation, then we get dou Ri by dou qj equal to dou Ri dot divided by dou qj dot. Then dou Ri is vi divided by dou qj dot. This is equation 9. Now substitute equation 8 and 9 in equation 7. Equation 7 is here. Now we can get the solution sum over ij pi dot dou Ri by dou qj del qj is equal to sum over ij d by dt of mi vi dou vi by dou qj dot. So in equation 7, dou Ri by dou qj, dou Ri by dou qj is replaced by the equation 9, dou vi divided by dou qj dot. Okay, and then minus mi vi dou vi here d by dt dou r by, this is d by dt dou Ri by dou qj is replaced by the solution dou vi dou qj. Therefore mi vi dou vi divided by dou qj del qj. Now we can write the kinetic energy of the particle here. So here also, therefore we can rewrite the equation sum over ij d by dt of mi vi square then remaining is dou by dou qj dot, dou qj dot. Similarly minus of mi vi square dou by dou qj del qj. Now rearrange the equation sum over j d by dt open the bracket here, sum over I separated from here, and sum over I of mivi square into dou by dou qj dot minus, and close the bracket, and dou by dou qj sum over I of mivi square and del qj. Del qj. Now put the term t is equal to sum over I of mivi square. Here this term or this term is replaced by capital T. Therefore the equation take the form sum over j d by dt dou, this term is replaced by t, dou t by dou qj dot minus dou by, this term is replaced by t, therefore dou t divided by dou qj, put the whole bracket here, del qj. So this is equation 10, this is 9 and equation 10. Now we put the value of equation 10 in equation 6. So this term is replaced by this solution. Therefore we can rewrite the equation 6. Now substitute equation 10 in equation 6. Therefore equation 3 become as sum over j qj del qj minus, we put the term from here, equation 10 sum over j d by dt dou t by dou qj minus dou t by dou qj dot here, then dou t by dou q j del qj. That is equal to 0. This is equation 11. Again we can rearrange the equation as sum over j d by dt dou t by dou qj dot minus dou t by dou qj minus qj into dqj is equal to 0. Therefore the equation take the form d by dt dou t by dou qj dot minus dou t by dou qj equal to qj, where j is equal to n. So because the form of final equation 12, already we know that generalized coordinates are independent of each other. So qj is independent of each other, and then del qj, that is del qj is equal to virtual displacement. It does not depend on time. This is does not depend on time. So this is coordinate dependent, therefore qj is vanish. Therefore the final solution we get in the Lagrangian form based on the D'Alembert's principle. So finally we concluded that this equation applied for constraint and holonomic system.